Good evening, everyone. Yeah. So, yeah, I think let's begin the session today. Can you all hear me? Yeah, okay. Okay, so we will begin the session today. So, this is the lecture for week 6. So, we will solve, as earlier, we will solve a set of problems related to some linear transformation and something related to vector space and all. So, let me share the screen first. Is my screen visible? Is the screen visible to everyone? Okay. So let us start with this problem. So the first question is, we have given two maps. Both maps are from R3 to R2 and it is defined as this. So the question is to check whether these two maps are linear transformation or not. So we know how to check the linear transformation or not. So if T is a linear map, it should satisfy T of x plus y equals T of x plus T of y and T of Cx equal to C into T of x, where C is a scalar, x, y are all vectors. So first we have the T. First one is T from R3 to R2. It is defined as T of xyz equals x square mod y plus z for all x, y, z in R3. Okay. So, what do you think? Is this a linear map or not? Is this a linear map? From the name linear itself, we can say it should be some in the form of linear combinations. Here we have one x square here. X square means it is not linear. It's having some power. Usually, if terms are coming like x square, x cube, and so on, it will not be a linear map. Okay, so here it will not be a linear map. So we will check one example. Okay, so I am taking t of 100. Okay, what is t of 100? Can anyone tell? Yeah, 10. We are just applying the map t of 100 equal to 10. Now I am taking the constant 2 and vector 100. That is t of cx. That is t of 2 into 100. This is t of 200. So by the definition of T map, we will get x square. Here x square means 2 square. This is 4 and mod y plus z. This is 0. If T is linear, T of 100 should be equals 2 times T of 100. 2 times T of 100 means what is T of 100? This is 10. Okay. This is 2 times 10, which is 20. That means these values are not same. These are not equal for 0 and 20. That is T of Cx equals C into T of x. This condition is not satisfied. Okay. This T does not satisfy this condition. So T is not a linear map. So here I have taken one scalar multiplication example and we get this is not linear map. In the same way, you can just check with the vector addition also with like two vector t of x1 y1 z1 plus x2 y2 z2 equals t of x1 y1 z1 plus t of x2 y2 z2. Like that also you can check. Now let us go to the next one. The second map is T. Again T is from R3 to R2. And this is defined as T of xyz equals x plus y, y plus z. Okay. So what do you think, is this T is linear or not? We will check. Okay. For that we need to check the addition and multiplication cases. So I am taking two elements. Let two elements A, B in R3. That is, these two are vectors in R3. What I want to prove is T of A plus B equals T of A plus T of B. Okay. Since A, B in R3, suppose A equals x1, y1, z1 and B equals x2, y2, z2. So, what is A plus B? A plus B is x1 plus x2, y1 plus y2, z1 plus z2. Then, what is T of A plus B? T of A plus B means T of, in the position of x, we have now x1 plus x2. In the second position, we have y1 plus y2 and z1 plus z2. So, by definition, what will be this value? What will be the value? Anyone? T is actually on xyz. If T we are applying, what we are getting is x plus y, y plus z. Here in the same way, in the position of x, we have x1 plus x2. In the position of y, we have y1 plus y2. So, what we will obtain is x1 plus x2 plus y1 plus y2. That is, we are adding x coordinate and y coordinate. In the second term, we are adding y coordinate and z coordinate. Here, this is y coordinate, y1 plus y2. And z coordinate is z1 plus z2. Okay. This is our T of A plus B. Now, what is our T of A? It should be equals T of A plus T of B. I am just considering T of A plus T of B in this side. What is our T of A? T of A means T of x1, y1, z1. Okay. T of x1, y1, z1 plus T of x2, y2, z2. So from this we can write T, like the value of this is x1 plus y1, y1 plus z1 and T of x2, y2, z2 means x2 plus y2 and y2 plus z2. So this is usual coordinate wise addition. We can add this as x1 plus y1 plus x2 plus y2 and y1 plus z1 plus y2 plus z2. Okay. So you can just check. Here T of A plus B we got x1 plus x2 plus y1 plus y2. Here also x1 plus x2. Just the arrangement is different but both are same value. T of A plus B and T of A plus T of B. Okay. So we are getting T of A plus B equals T of A plus T of B. Okay. So the next condition is T of CA. What we want to prove is T of CA equal to C times T of A. Okay. What is T of CA? That means T of C times x1, y1, z1. This is equals T of Cx1, Cy1, Cz1. Okay. What will be the value of this one? Yeah, someone has raised the hand. Anyone is having doubt in between? Roja Bharat, do you have any doubt? Okay, then. Okay, let me continue. T of CA is, yes. Can you repeat, please? Yeah, we need to check both the conditions here. No, no, no. Like otherwise we can check like this. T of Cx plus dy equals C times Tx plus d times dy. If we are checking, no, it should be true for all C, not just one C. Any C we are saying. That's why we are taking in general any C scalar in the field F. Yeah, we need to check both the condition like separately like this, or you can check like this also, means combined. Both conditions are combined, scalar multiplication and the vector addition here combined. Okay, so here I am checking separately. So here T of CA is, we got this one. So by definition of this, what we will get is Cx1, that means x coordinate and y coordinate we are adding first, and the second term is y coordinate plus z coordinate adding. From here, actually, we can take the C outside. C times x1 plus y1 and y1 plus z1, which is nothing but T of x1, y1, z1. This is our A. That is C times T of A. Okay. So, we got both the condition. That means T of A plus B equals T of A plus T of B, and T of CA equals C times T of A. Here A, B are vectors in R3 and C is a scalar. It is in R. Means whatever the field we are taking, I think here it is field. Okay. Means T from R3 to R2 means we are assuming the field is over R. Okay. So what we are getting is the second one is a linear transformation and first is not a linear transformation. Is this clear for everyone? Yeah, if it is clear, let's go to the next problem. Here we have two subspaces, U and V, U and W are subspaces of R3. What is U? U is written as the span of two elements in R3, that is 1, 2, 1 and 2, 1, 3. Okay. In the same way, W is also a span of 1, 0, 0 and 0, 0, 1. Okay. Um, so, what will be the dimension of U? Can anyone tell what will be the dimension of U? And in the same way, dimension of W? Yeah, yeah, dimension is 2. Okay. In both case, dimension is 2. So if anyone is having doubt, you can just check whether these two elements, that is 1, 2, 1, 2, 1, 3 are linearly independent or not. Already this is spanning set and we just need to check the condition whether it is linear independent or not. So obviously it will be linearly independent, otherwise one will be a multiple of other. Here 2, 1, 3 is not a multiple of 1, 2, 1 and 1, 2, 1 is not a multiple of 2, 1, 3. So it cannot be linearly dependent. So it is a linearly independent set. In the same way, 1, 0, 0 and 0, 0, 1 are linearly independent. So in both case, we are getting dimension of U and dimension of W are 2. Okay. Now the question is dimension of U intersection W. So we have one theorem, dimension of u plus w equals dimension of u plus dimension of w minus dimension of u intersection w. Okay. Okay, I will say. So here we have two elements, 1, 2, 1 and 2, 1, 3. So I am taking the linear combination of 1, 2, 1 and 2, 1, 3. Okay. Then I will equate this linear combination to 0. Means 0 element in the, here 0, 0, 0 is our 0 element. Okay. Now I will do this. Means C1 plus 2C2, 2C1, just adding by coordinate ways. 2C1 plus C2 and C1 plus 3C2. So this we are equating with our 0 element 0, 0, 0. That means C1 plus 2C2 equals 0, 2C1 plus C2 equals 0 and C1 plus 3C2 equals 0. From this we can C1 equals minus 2C2 and here C1 equals minus C2 by 2. Okay. So we will check these two conditions. From this we are equating this 2C2 means C1 equals minus 2C2 and C1 equals minus C2 by 2. So we can equate these two. Okay. That means 4C2 equals minus C2 implies 3C2 equals 0. The only possibility is C2 equal to 0. Since C2 equals 0, C1 is also 0. Okay. C1 is minus 2C2. So, yeah. C1 is minus 2C2. And we got C2 equals 0. Is that clear? Yeah. So, if we are writing these two elements as a linear combination like this, and if we are getting both the coefficient as 0, that is, this is the representation. This is the only representation like this, means linear combination with both the coefficient are 0. If such a condition is satisfied, we will say linearly independent, right? Okay. So that is why it is a linearly independent set. In the same way, you can check this set also, linearly independent. Okay. Anyhow, we got dimension of u and dimension of w as 2. Now I am considering u intersection w. So, of course, dimension of u, u intersection w will be a subspace of u and w. Okay. So, dimension of u intersection w will be less than or equal to dimension of u, which is same as dimension of w. Okay. This is 2. So, what are all the possibilities of dimension of u intersection w? Yeah. Possibilities of dimension of u intersection w are 0, 1, 2. So, let us check the first case. First case is, suppose I am checking dimension of u intersection w equals 0. Okay. Now, we have theorem dimension of u plus dimension of w minus dimension of u intersection w equals dimension of u plus w. Okay, what is in the LHS? Dimension of u is 2 and dimension of w is also 2 minus, we are assuming dimension of u intersection w is 0. This is 0. That means this is equals 4. What it says is dimension of u plus w is 4. Is this possible, this condition? Can dimension of u plus w equal to 4? The question is here u and w are subspaces of R3, right? U, w are subspaces of R3. So what about u plus w? Will it be a subspace? Whether u plus w will be a subspace or not? No, u plus w will be a subspace always, because u plus w is set of all u plus w. I think this already proved in the class. U in u and w in w. It will be a subspace. Okay, you can check if you want. Like we have already one condition, right? If it is a subspace, like if I am taking two elements in u plus w, that is a, b in u plus w, I can write a as some u1 plus w1 and b as some u2 plus w2. Okay, let me take x and y. I am taking x and y in u plus w, and I can write x as some element u1 plus w1 and y as u2 plus w2. I am taking ax plus by, where a, b are scalar, a, b in field F. Ax plus by means a into u1 plus w1 plus b into u2 plus w2. Okay. From this, I can write a u1 plus bu2 plus a w1 plus bw2. So this is an element in U, capital U means our subspace U, and this is an element in W. So this ax plus y by is an element of our U plus W. Fine. That means I am taking two elements, then their linear combination is also in U plus W. And U plus W is a non-empty set, because all elements in U, all elements in W will also be in U plus W. Okay. So this condition ensures U plus W is a subspace. So what is the maximum possible dimension of U plus W? Yeah, 3. Maximum possible dimension of U plus W is 3. So now what do you think here from this? If we are assuming dimension of U intersection W equal to 0, what we are getting is dimension of U plus W is 4 by this theorem, right? Is this possible now? Is this possible? Yeah, no, because the maximum possibility is 3. So this is not possible. So where we are wrong is we have taken this dimension of U intersection W as 0. So this is not possible. So we have two possibilities remaining, 1 and 2. Now let me go to the next case. Case 2. I am assuming dimension of U intersection W equals 2. Okay. We already know that dimension of U and dimension of W are 2. Right? And U intersection W is a subspace of U and W. Fine. So the only possibilities we are having is U intersection W equals U equals W. Right? But is this U and W equals? See, this is our U. U is span of 121, 213, and W is span of 100, 001. Is this both are same? Yeah, this basis is different also. Like if we are taking any, what can I say is, if I am taking any element 1 to 1, 1 to 1 is an element of U. I cannot write it as a linear combination of 1 0 0 and a 0 0 1, because here in both the 1 0 0 and 0 0 1, the y coordinate is 0. Okay, so if y coordinate is non-zero, I cannot write it as a linear combination of these two elements. Fine. So there will be some element in U other than in W. In the same way, there will be some element in W other than in U. This U and W are not same. So if we are assuming U intersection W, dimension of U intersection W is 2, then also we are getting a contradiction. Uh, because U not equals W. Is this clear? Any doubt here in the second case? So we removed the two cases, that is dimension of U intersection W equals 0 and dimension of U intersection W equals 2. So the only possibilities is 0, 1 and 2. We removed the 0 case and 2 case. So the only possibility is dimension of U intersection W is 1. Dimension of U intersection W is 1. Is this clear for everyone? Or I will do in one more way, alternatively. So again, I will use the same theorem, that is dimension of U plus W equals dimension of U plus dimension of W minus dimension of U intersection W. We need to find dimension of U intersection W. This is equals dimension of U plus dimension of W minus dimension of U plus W. Okay, so these first two values are non-values. We already found these both are dimension are 2, 2, 2. Okay, but we don't know what is dimension of U plus W. So U plus W equals set of all U plus W where U in U and W in W. Okay, that means all elements which spans U and all elements which spans W. We are taking all such elements and together the span of these both set together will be our U plus W. So we know that for U we have span of 1 to 1 and okay, 1 to 1 and 2 1 3. This will span all U. Okay, all W will be spanned by 1 0 0 and 0 0 1. Okay, all together all 4 elements will span our U plus W because their combination will give the elements in U plus W. Fine, but here it is not linearly independent. This is clear because in R3 the maximum possible linearly independent element is 3. So I am just considering 3 elements here. For example, 1 0 0, 0 0 1 and 1 2 1. Okay, so here if I am finding the determinant, what I am getting is 1 minus, which is equals minus 2. Okay, that means I am taking this element, and this element. So these 3 elements here, the determinant is non-zero, means these 3 elements are linearly independent. Okay, so we got linearly independent spanning set because we don't need to consider the 2 1 3. Obviously all these 3 will generate our R3. So we don't need an extra 2 1 3. Okay, so we are checking for the minimum elements. So what we are getting is U plus W is span of 1 to 1, 1 0 0 and 0 0 1. Okay, so this is spanning set and a linearly independent set. So this is a basis. So 3 elements spans the set means this is our full R3, right? So U plus W is our full R3. So what will be dimension of U plus W? It will be equals 3. Fine. Okay, so we got all the values here. So from this, what we are getting is dimension of U intersection W equals dimension of U2 plus dimension of W2 minus dimension of U plus W, which is 3. This is 1. Okay. In this way also, we will get dimension of U intersection W is 1. Okay. Is the problem clear for everyone? Anyone is having doubt here in this problem? Okay, if you are not having doubt, let us go to the next one. So, all the 4 elements. Hmm. Like U plus W, as I already told, it is a subspace of R3, right? So 4 element is linearly independent. This is not possible, right? So maximum is 3. So I'm just checking with the 3 elements. Like already I know 100. Simply by looking at this, I can say 100 and 001 are linearly independent. So I just trying to add one more element from here. Then also this set of 3 elements is linearly independent. Okay. So I got 3 linearly independent elements which spans our U plus W. From this we can easily conclude U plus W is nothing but our R3. Right? Yeah. Okay. So let's go to the next problem. Here we have given 2 statements. Okay, we need to check whether it is true or not. So first we have given first statement is S is V1, V2, etc. Vn. This is a subset of V. V is our vector space and the question is span S is a subspace of V or not. So what do you think, span S is a subspace of V or not? So how will you check whether a set is a subspace or not? What is the theorem? Anyone please? How can we check whether a non-empty set is a subspace or not? Is this span S non-empty? Can you repeat? The only thing in the theorem says is the subset we are considering should be non-empty and one more condition should be satisfied. 0, will always belongs to subspace, but we don't need to check. Of course, 0 will belongs to that subspace, but we don't need to check. We just need to check at least one element is there or not. Then we can check the other condition. What other, like here span S is non-empty, right? Product of 2 elements. 2 elements means where you are taking the product. Can you specify? This vector product is not possible. As of now, we haven't told anything about vector product. We have scalar multiplication. About which product you are talking? Can you clarify once again? Can you tell once again what's your doubt? Okay. Here span S is a non-empty set because V1, V2, etc. Vn all in S. So it will be in span S also. Okay. This is a non-empty set. And also if you have doubt whether there is a 0 or not, what is span S? Span S means set of all linear combination. I can take 0 V1 plus 0 V2 plus etc. plus 0 Vn. Okay, this is obviously our zero element which belongs to span S. This is a linear combination of elements in S. So this will belongs to span S, right? So 0 is an element of span S. So in this way also you can verify 0 is an element in span S and span S is non-empty. Anyhow, the only thing is we need to check whether there is an element in span S. First of all, there is an element in span S. Okay. Now to check this span S is a subspace of V, we need to check if we are taking two elements x and y in span S, ax plus by belongs to span S or not. Okay, where a, b are scalars in the field F and x, okay, x, y already taken in the span S. Okay, so if this condition is satisfied, then only we can say this span S is a subspace. So we have two conditions. One thing is the subset is a non-empty subset and this condition should be satisfied. Right? So let us check whether this condition is satisfied. So x and y in span S. So I am taking x as sigma ai vi where I varies from 1 to n. X is an element of span S. So it can be written as the linear combination of v1 etc. vn. That is written a1 v1 plus etc. an vn. And I can write y as sigma bi, some other combination of vi's where I is 1 to n. Okay, y is also in span S. So y is written as linear combination. So what will be our ax plus by? Ax plus by a times summation aivi where I from 1 to n plus b times summation bivi where I varies from 1 to n. Right? So I am taking the coefficients of vi together. For the vi, the coefficient is a times ai plus b times pi. Right? Sigma I equals 1 to n a times ai plus b times bi of vi times vi. Okay. So this is also a linear combination. This is a combination of v1 etc. vn, right? So this also belongs to span S. Okay. So we got span S is a non-empty subset and this condition ax plus by. This also belongs to span S for any xy in span S and for any two scalars AB. Okay. So span S is a subspace. This is the only thing we need to check whether a subset is a non-empty subset is a subspace. Is this clear, everyone? If you have any doubt, you can ask. Is this clear? Okay. Now we have one more thing here. So, okay. The statement 2 says if U and V are two vector spaces with a finite dimension, then U and V are isomorphic if and only if dimension of U equal to dimension of V. This statement actually it's already covered in the lectures. So I am not going to repeat the proof. So this is a theorem. This is a theorem statement. If U and V are two finite dimensional vector spaces, U and V are isomorphic if and only if dimension of U equals dimension of V. So you can just refer to that class again. So statement 1 is true, already we proved. True. statement true also. So true. It is already done in the class. Okay. So can we go to the next problem? Anyone is having doubt? Okay, if you have no doubt, let me go to the next problem. Here, again we have given a vector space M2R, where M2R is the set of all 2 by 2 real matrices. That means M2 of R means something like set of all A, B, C, D. This is 2 by 2 real matrices, where A, B, C, D are elements of R. Okay, and we have given a linear transformation. This is our vector space M2 of R. From this vector space to the same vector space M2 of R, the linear transformation is given as T of A, where A is a matrix like ABCD, something like ABCD. Okay, any matrix A is mapped to A plus A transpose by 2. Okay, here A is a 2 by 2 matrix, A transpose is a 2 by 2 matrix. So summation, we are taking the summation and dividing each coordinate by 2. So this is also a 2 by 2 matrix. So it will also belongs to our M2 of R. Okay, so this is our function. So anyone is having doubt whether T is linear or not? Actually, T is linear, it is easy to check. T is linear. Okay, let me check once. If I am taking any A and B, where A and B are in M2 of R. What is T of A plus B? A plus B is a matrix. So, by definition, A plus B plus A plus B transpose by 2. Okay. Here I can write it as A plus B plus A plus B transpose is same as A transpose plus B transpose. Okay. This is one basic result. You can just check if you want. And this divided by 2. So, from this we can write this A plus A transpose by 2 plus B plus B transpose by 2. Okay. So, this is our T of A. By definition, this is T of A plus this is our T of B. So, T of A plus B equals T of A plus T of B. Now, in the same way, I am checking for one scalar. T of CA equals CA. CA is a matrix, means each entry of A is multiplied with C. So, T of CA equals CA plus CA transpose by 2. This is our definition. Okay. This is same as CA. CA transpose we can write C times A transpose by 2. Okay. So, which is equal C times A plus A transpose by 2. This is C times T of A. So, both the conditions of linear transformation is satisfied. So, T is linear. Now, we just check the condition T is here actually already given it is linear transformation. So, we just checked, we just verified it. Okay. Now, the question is the dimension of kernel of T and dimension of image of T. We need to find both these values. First, let us go to the kernel of T. What is kernel of T? If T is a linear transformation given above. Okay. By definition, what is kernel of T? I want response. Yeah. Yeah, dx equal to 0. Here, T is a map from matrix M, set of all matrix, right? So, we can take it as matrix, set of all A, such that T of A equals 0. 0 is our, I am writing this as 0. This 0 is 0 matrix. Okay. 0. Okay. So this is set of all matrix A. By definition, what is T of A? A plus A transpose by 2 equals 0. So we need to find the all such A which satisfy this condition. Okay. So we will just see this condition. A plus A transpose by 2 equals 0. Which is same as A plus, okay, you should note that this 0 is a 0 matrix, not our usual 0. That means A plus A transpose is our 0 matrix. 0, 2 by 2. Okay. This A plus A transpose is 0 matrix means A equals minus A transpose. Okay. So, suppose my A is A, B, C, D. That means A should be equals minus of A transpose. What is A transpose? AC, BD, right? Because we are just interchanging the rows and column. So this condition, this A plus A transpose by 2 equals 0 is same as this condition. Okay. So we are equating. Equating means A should be equals minus A, B should be equals minus C, C should be equals minus B, and D should be equals minus D. A and minus A equal means only possibility is A is 0. And D and minus D equal means D is 0. Right? So, the only two condition we are having is B equal to minus C and C equal to minus B. Means this is same condition. Both are same condition actually. Okay. So, A should be in the form. So, we got values for all these A, B, C, D. A is 0 and D is 0. If I am taking one B, then C is depend on this B. That C is our minus B. Okay. That means we are having only one variable here because A and D are 0 and B is a negative of C. So we have only one variable. Okay. If A is in this form, then only we got T of A equals 0. This is the only form. This actually generated by only one matrix. I am taking any entry. I am just taking 1 and minus 1 here. Okay. I am taking span of this matrix. This is our kernel of T. Okay. This is a single element, a non-zero element. So this is linearly independent. And we got any element in kernel of T is of the form 0, B minus B 0. So we will just take the scalar multiplication. That is, the just scalar multiplication is our linear combination here. Okay. So this span of this element is our kernel of T. Is this clear, everyone? Last one. Okay, up to this portion, it's clear. Okay. Yeah. So we got any element. We are taking A is in. We are starting with kernel, right? This condition we are starting. So we are ending in A should be in this form. Okay. So if I am having an element 0, 1, minus 1, 0, I can generate any element of the form 0, B, minus B, 0. Because only thing I need to do is multiply the 0, 1, minus 1, 0 with B. Then I will get this element. Okay. So I am taking multiplying with a scalar multiplication means this is the span of this one. Okay. Here I have only one element. I am just taking the all scalar multiplication of this element. I will get all possible this elements. That means all elements in the kernel of T. Okay. So our kernel of T, this is a linearly independent also. Because it is only one non-zero element. It is always linearly independent. Okay. So kernel of T, we can write it as span of this element. This kernel of T is a subspace which can be written as span of only one element. That is, this is the basis, or I can write it as B equals 0, 1, minus 1, 0. This set is a basis for kernel of T. Is this clear now?
Yes.
Okay. Then what will be the dimension of kernel of T?
1.
1. Right. Dimension of kernel of T is 1. Okay. So we got the dimension of kernel of T. Sorry. Okay. So here dimension of kernel of T is 1. Now T is a map from M2 of R to M2 of R. Okay. What is rank nullity theorem? Rank nullity theorem? Rank nullity theorem? Ah, yeah. Dimension means for a vector space, not for a transformation. Equals this will no dimension of M2 of R. Yeah. If T is a map, like from where we are starting the T, this one we will take. Okay. If T is from U to V, we will take rank T plus nullity of T equals dimension of U. Rank T plus nullity of T equals dimension of U, not dimension of V. This one. Okay. So here both are same. We are taking dimension of M2 of R. Okay. Now we already got nullity of T. What is nullity of T? Dimension of kernel of T, right? Nullity of T. Nullity of T means dimension of the space kernel of T. That we got already one. Okay. Now we want to find rank of T also. What is dimension of M2 of R? Anyone? Yeah, 4, right. Dimension of M2 of R is 4, right. Okay, I will tell you how dimension of M2 of R. M2 of R, as I already told, it is something like ABCD, set of all matrix of the form ABCD, where A, B, C, D are elements of R. Okay. So here we have 4 variables. Corresponding to A, we have one matrix. Like what I can write is, it can be written as span of 1, 0, 0, 0. I am just considering the first element only. So I am generating the first element using this matrix. So, and for the second element B, I am considering 0, 1, 0, 0. Okay. And third element C, I am considering 0, 0, 1, 0. And for the fourth element 0, 0, 0, 1. Okay. If I am having any element like M2 of R means set of all matrix of the form A, B, C, D. If I am having any ABCD, I can write it as A 1 0 0 0 plus B times 0 1 0 0 plus C times 0 0 1 0 plus D times 0 0 0 1. Okay, that means any matrix ABCD, I can write it as span of these elements. Is this clear? And also this set is linearly independent. Okay, for linearly independent also we can check. If I am taking the linear combination of these 4 elements, C2 times 0 1 0 0 plus C3 times 0 0 1 0 plus C4 times 0 0 0 1. If I am equating it as 0 matrix, what I will get is, I am just adding, I will get C1, C2, C3, C4 equals the 0 matrix. Okay, that implies CA equal to 0 for all I 1, 2, 3, 4. So this condition ensures this is a linearly independent set. So this is a linearly independent set which spans whole M2 of R. Okay, so we got a basis. So what is dimension of M2 of R? Dimension of M2 of R, as you said earlier, it is 4.
4.
Okay. We have rank T equals, so from the rank nullity theorem we will get rank T equal dimension of M2 of R minus nullity of T. This equals 4 minus 1. This is 4 and nullity already found 1. This is 3. Okay. Rank of T is 3. So in our question, so dimension of kernel of T is 1. Rank of T means dimension of range of T or dimension of image of T. So that is 3. We got it. Okay. Anyone has doubt here? Okay. Yeah. Image of T means same, range of T. Image of T means set of all. Image of T means set of all Tx such that x, like if T is from U to V. Image of T means set of all Tx where x is an element of U. Okay. This is same as range of T. Like this is just term, two terms representing the same set. So what rank of T means? Equal to dimension of range of T, or we can say dimension of image of T. Okay. Is this okay now? Okay. So any other doubt? Okay. So I think we can solve one more problem. Okay. Let me go to this problem quickly. So we have given T from R3 to R5. Okay. And this is given as a 1-1 map. Okay. Then option A. Is option A possible? Like here is they are saying rank is 5 and the nullity is 2. Before that, again we will solve this problem using rank nullity theorem. Here what is rank T plus nullity of T? What is this by rank nullity theorem? Dimension of R3. Yeah. What is dimension of R3? 3. Right. So we got rank T plus nullity of T should be equals 3. This is true for any map T. Okay. Now, is the condition A is true? Here they are saying is rank is 5 and nullity is 2. Is this possible? This is not possible. So, yeah, we are discarding this condition. Okay. Now, what about B? They are saying rank and nullity can be any pair of non-negative integer that add up to 5. Is this true? No. It should be add up to 3, right? Yeah. This is also false. B is also false. So, now C. Rank is 2 and nullity is 3. Is this true?
No.
No, again this is not true. Rank 2 nullity 3 means total sum is 5. Sum should be equals 3. So third condition is also false. Now of course D is true because all others are false. Or we can say rank is 3 and nullity of 0. Rank 3, nullity 0, which is equal to 3. This is true, right? Okay. And one more thing here. Actually, here T is a one-to-one map. Okay. So always the nullity of T should be 0. So this is the only possibility here. Like actually to get 3, I can write it as 2 plus 1 equal to 3 also. Okay. In that case, my rank should be 2 and nullity should be 1. But here, since it is given T is 1, 1, we cannot take this case. This is not possible. Okay. If T is not 1, 1, we can take any case such that the sum rank T plus nullity of T should be equals 3. So we can take a pair 1, 2 or 2, 1, whatever. Okay. Since because it is T is 1, 1, this nullity should be 0. So this is the only possibility. The D is the only possibility. So D is the right answer. Okay. Is the problem clear for everyone? Yeah. Anyone is having doubt in any of the problems? If you have, you can ask now. Just I didn't get you. Can you repeat? Okay, okay. Slide number 3. Okay. Question number 3. This one? Okay, okay. Sec- yeah. Second statement actually I didn't explain because in one of the lecture it is clearly proved. This is actually a theorem. So in one of the lectures by sir, it is already explained. It is proved. All the proofs are there. So you can just refer that lectures. Yeah. Yeah, this is a theorem. Okay, okay. Okay. Any other doubt? Okay, if you don't have doubt, you can leave the meeting. We will meet in the next week. Again, Monday, same time, 6 to 7. Or if you have doubt, you can ask now. Yeah. Nullity. Nullity of a transformation means all elements in the, like if T is a map from V to V, if T is a map from any U to V, U and V are vector space, what null space of T? Null space of T, or we will say it as kernel of T. Same, both are same. These are all set of all elements in U which going to 0. Under the map T, if x going to 0, then it is in the null space or kernel of T. Okay. Now, nullity means the, the dimension of the null space. This is a space and the nullity is the dimension of the null space or dimension of kernel of T. Is this okay? Your doubt is fine? Yeah, for 1 1 map it is just 0. If T is 1 1, 1 1, kernel of T will be just 0 elements. So nullity of T is the dimension of kernel of T. For 0 space it is 0. Okay. Clear? Yeah. Any other doubt? Okay, so let me stop the session today then. So we will meet the next week. Thank you everyone for attending. We will see next week.